The alkene 3-methyl-pent-2-ene reacts with hydrogen bromide to form a mixture of 3-bromo-3-methyl-pentane and 2-bromo-3-methyl-pentane. The alkene 3-methyl-pent-2-ene exists as EZ isomers. Draw the structure of the Z isomer. So what I'm going to do first, I'm just going to sketch out and think, what does this look like? So we've got this C with the double bond in it, and we've got a H and a CH3, and we've got a CH. So on the left we've got a H. This may not be the Z isomer. I will cross this out when I've done my working out. And on the right hand carbon I've got a CH3 and a CH2CH3. Now what I'm going to do is I'm going to think about the SIP rules. And the SIP rules say take each carbon in turn. So I'm going to take this left hand carbon. I'm going to look at what's attached. This has atomic number 1, hydrogen, and carbon has atomic number 6. So this has highest priority. Then I'm going to look at the right-hand side carbon. They're both a carbon, so they're both number 6. So I'm going to move along the chain. Hydrogen is 1. First point of difference is we've got a second carbon. So this is the highest priority. Now you can see that I've got my two highest priority groups on the same side. So if they're on the same side, Z is on the same side, Z is the Z. We're going to say this is the Z isomer, so I'm just going to draw that out a tiny bit neater and then cross through my working for the exam board. So I want my double bond nice and clear with my 4 groups, trigonal planar. I'm just going to tidy that one up around each carbon. So on my left hand carbon here I've got a hydrogen and a methyl group, and on my right hand carbon I've got a methyl group and an ethyl group, and I've got my ethyl group and my methyl group on the bottom here on the same side of the double bond, and therefore this is the Z isomer. Okay, this was just my working out, so I can cross through that for the exam board and then move on. Name and outline the mechanism for the formation of 3-bromo-3-methyl-pentane. Okay, so I'm going from my 3-methyl-pent-2-ene and I'm ending up at 3-bromo-3-methyl-pentane. Okay, now unfortunately they've given us lines here in which to draw a mechanism, which is not the easiest, but we can draw over the lines. So we have to name and outline the mechanism. So this is an alkene mechanism. We're using HBr and an alkene. Alkenes are an area of high electron density, so electrophiles are attracted to them. So we're going to have an electrophilic reaction, and we're just adding the hydrogen bromide, nothing is falling off. So it's an electrophilic addition. I'm going to redraw out my alkene. So this is the alkene that we had. Okay, and the hydrogen bromide, we do need the hydrogen close to the double bond because the hydrogen is the element that's less electronegative than bromine and therefore would be the delta plus, and that would be attracted to the area of high electron density. I'm going to draw a curly arrow from where the electrons are. Remember, a curly arrow shows movement of a pair of electrons. It must start from either a lone pair or a bond pair, a shared pair. In this case, it's going to start from the shared pair of the pi bond, and it's going to go to the hydrogen atom. And then the HBr bond is going to break and put the electrons onto the Br. So now we need to figure out where we're going to put everything. My top tip is to redraw the 2 carbons of the double bond, but you've broken the double bond. Move everybody around. So imagine you were doing a starfish shape and now you're doing the box splits. Everything's moved around and up. So the H that was pointing up and left is now straight up, and the methyl group that was down there is pointing across. Then we had a methyl group pointing up and right. It's gone right up and opened up the double bond. So we've opened up the double bond. Now we need to put the H that we've attacked as our electrophilic attack on the correct carbon. So you can do this one of 2 ways, but I would suggest for this question, rather than trying to decide which is the most stable carbocation intermediate, just look at the product that you're trying to produce. So up here, we're trying to put the Br onto the same carbon as this extra methyl group, and so that must be where the positive carbocation positive charge is, because that's where the Br needs to go in the next step, and the hydrogen must be going on the left hand carbon of the double bond, because that's what our product is showing us to produce. This actually also happens to be the major product formation route, because this is the most stable carbocation intermediate. I'm going to talk about that in a little bit. Now we're going to take our bromide ion. Remember that when we did this second curly arrow over here on the left, this over here, then we were putting a pair of electrons onto the bromine. From the bond pair became this lone pair on the bromine, and now they're going to go in and attack that carbocation to join on. So we can finish off our mechanism and form 3-bromo 3-methyl pentane. So there we've got our mechanism. And then the last part of the question, explain why more of this particular product is formed than 2-bromo 3-methyl pentane. So 3-bromo, so the one that we have formed, 3-bromo 3-methyl pentane. And you must get your language correct here. 3-bromo 3-methyl pentane is formed from, it isn't the carbocation, it's formed from, and it was formed from a, here's the plus, 1, and it's got 1, 2, 3 C's attached. It's formed from a tertiary carbocation intermediate. Okay, whereas our other product, which we're calling 2-bromo 3-methyl pentane, is formed from a secondary running out of space here, but if you were to draw that out, if you were to look, you would have put the plus on the other side, so it would have been a CH3 and then a C with a H and a plus, and then a C with the methyl group and the ethyl group. That would have been the secondary carbocation intermediate. We don't need that in our answer, I'm just going to delete that. And the tertiary carbocation intermediate is more stable. So some sort of shorthand, I'm going to use like a 3 degrees, is more stable than secondary, as it has 3 alkyl groups rather than 2. Alkyl groups have what we call a positive inductive effect that stabilises the positive charge.